For a moment, and welcome, Maya. And we are very pleased to welcome you to these days of combinatorial optimization and polyhedral theory. We are sorry for the delay, and I will present you to the public, and then I let you give your talk. Thank you. So today we are going to listen to Maya Stein, who is a full professor at the Department of Mathematical Engineering and research at the researcher at the Center of Mathematical Modeling at the Universidad de Chile. She is a specialist in graph theory and combinatorics. She's editor-in-chief for Electronic Journal of Combinatorics and member of many scientific programs. And I let Maya give us some news and some elements about minimum degrees and tree subgraphs. Can you?
Yeah, thank you very much. Je parle un peu de français, mais c'est pas suffisant pour faire la présentation en français.
Vous auriez dû me dire à l'avance.
Bonjour Maya, merci beaucoup d'être avec nous aujourd'hui. C'est Rida Majoub qui parle.
C'est notre grand organisateur.
Maya, you are hearing me?
Yes, yes.
Yeah, donc vous parlez français un peu?
Oui, je parle un peu, mais je crois pour la présentation, il me manque des mots techniques.
J'ai voulu te remercier beaucoup d'avoir accepté notre invitation.
Merci pour
on est très content de te voir un peu parmi nous aujourd'hui et de nous faire cette présentation. C'est très gentil de ta part et merci beaucoup pour ta disponibilité. Merci beaucoup.
Non, moi, je suis enchantée. Merci pour l'invitation. C'est dommage que je n'ai pas une excuse pour visiter la France. Et vous, mais c'est comme ça.
La COVID-19 qui nous oblige un peu d'être confinés un peu chez soi et de faire tout à distance. Sinon. D'ailleurs, moi, j'ai un projet en fait avec le Chili et avec le Brésil depuis 2 ans et j'ai pas pu aller avec Ivana Lubitsch et Eduardo Ischua. Je dois aller au Chili et à cause de Covid, on n'a pas pu.
Oui, j'ai compris. C'est dommage. Oui, c'est la même chose pour moi aussi à l'envers. Je crois que tout le monde, mais ça va passer un jour.
Ok. Aujourd'hui, on a une grande spécialiste des graphes et de la combinatoire qui est avec nous aujourd'hui.
Alors, peut-être I can start. So I will switch now because I really don't know the words probably, and it will take much longer. I have to say it in French. Yeah, but if you have any questions also, you can just, I can try to have a look at the chat, and you can also just say whatever you want, ask whatever you want to ask, just interrupt me, and I try to explain it again. And I think perhaps you can even ask in French, I don't know. But we will get through this somehow. So I'm going to talk about, let me get this in the right size. So I'm going to talk about something that I have worked on with several people. So there's just subsets of the people that I wrote below here. All of these, of which Guido was my student, and well, Nico was my student, and then he went to Europe. And Matthias, mainly it's a lot with Matthias Pavesine, and also some things with Bruce Reed that are there. And it's all about finding trees in a graph. So it's going to be a very theoretical talk somehow. So you're going to have to be prepared for that. We'll just look at at the structure of graphs and how the degree, minimum or sometimes average degree of the graph has an influence on possible subgraphs, subgraphs that the graph can have. So I'm going to talk first about the graphs, and then I'm going to talk about a little bit, if there's time, about hypergraphs and digraphs as well, because there have been some recent work. So the basic question, as I just said, is if you have a graph with a certain minimum or average degree, say, you know something about the degrees, then what subgraphs must appear? And I will, well, let's first look at what the classical theorems are, because I suppose you know that, but let's just go through these things. So many people know, do you see all of my screen? Because it looks to me like the bottom part is, this is better, right? So one of the oldest theorems in graph theory is Mantel's theorem, which says that with an average degree, so this is the average degree of about half the size of the graph in number of vertices, half the order of the graph, then the graph has a triangle. So this is just so that we see it again. Then more famous is probably Turan's theorem, which says the same, like it's a generalization of what Mantel had, but it's for all complete graphs. So he shows with this average degree, or this is basically density, edge density of the graph, you find a complete graph of that size in your graph. So it doesn't really matter the exact statements. I just want to the general spirit is I have some degree and I can guarantee something. And then we all know if the average degree is at least 2, then your graph will have a cycle, because trees or forests have lower average degree, right? So you know it is going to be there. But you don't know really the length of the cycle. So then probably you've seen, you know Dirac's theorem, which says if I want a Hamilton cycle, which is a cycle that goes through all the vertices of the graph, then I have a condition for that. And his condition is your minimum degree has to be n½ if n is the size of the graph, right? So the number of vertices of the graph. So you probably have seen that, but I'm going to remind you a little bit of one of the proofs of this theorem. So we can see how we can extend this a little bit. So the way I teach it, when I teach graph theory, I usually do this proof because I like it. So you take a longest path and you look at the end vertices of this path, and you notice that if it's a longest path, then the end vertices must have all their neighbors inside this path somehow. And then you just do a quick calculation and see that then there must be a structure like this, where this is a neighbor of that end vertex and this is a neighbor of that end vertex, and they are neighbors on the path. And then what you can do is you can make a cycle like this. And so if you didn't cover the whole graph, since your graph is going to be connected with this minimum degree, you will know that if you have some extra vertex somewhere out here, it is going to have to be, there has to be some connection. So you're going to have a neighbor of this thing here. And then you can make a longer path by just going around here and then going back here. It doesn't matter where that outside vertex connected to it, right? So this is and then it's a contradiction to that you took the longest path. And so you're done, right? So either you take the longest path, it's already the whole graph, you know how to make a cycle out of it, or you make the path longer, which gets into a contradiction. So this is the way you can prove Dirac's theorem, but you can also you can also ask yourself, can you extend this? Like you can first say, well, if maybe I don't want to talk about cycles and what's coming up, so let's maybe just talk about paths. This is going to be easier. So then you can actually like make this condition a bit, like make this number a little bit smaller, because if in the beginning you had a path of the right length, then you just stay with it. So it doesn't really matter, but you can take out a -1 here. And now you can ask yourself, how about shorter paths? So can I say something like this, the same thing, but maybe now I want, instead of this condition that is this number, like I want to put some k here, and I want to have a path of size k, right? So this is the question. If I have this minimum degree here, can I then say I find a path on k vertices or on k edges? Right, so I think yeah, that is right. So yeah, I think I then changed it on this slide. I don't know why, but then yeah, so it's the same thing, because now I changed it to k edges, and the degree condition is a bit lower. So what you cannot have, this is not true necessarily, because what goes wrong when you go in your argument, it may just be that this here happened in a component of the graph that was just too small to contain a graph on k vertices. So if I only have this condition here, then the whole graph G could be of size about k half, a bit more than k half maybe, and then you cannot find a path on k vertices, no way, right? So you need something more so you can make this argument work, but you can make it work, because the only point is, the part with finding the cycle is working just the same. The only important point is that you have to, if you don't have the length that you wanted, then you can make it bigger by finding someone who's a neighbor of this cycle that you found. So you can do that if the graph was connected and large enough, right? So if your graph is connected and has at least k vertices, then you can use the same argument to show this. And this is something I want to come back later to. So it's sort of, yeah, I don't know. It's just an observation that you get basically from Dirac's theorem, or from the way you can prove Dirac's theorem, and it's just that instead of Hamilton, you can just do it for a smaller path with a scaled down minimum degree, right? So now you can, instead of minimum degree, you can also look at average degrees. And so the first people who stated it like this, the theorem was Erdős and Galay, who well, there is this theorem. They also wrote something about cycles and so on, but let's just look at the path. So they said, if you have an average degree at least this, so more than k -1, then your graph contains a k edge path. So how do you prove this? Well, you just apply a lemma that is sort of folklore, which you probably also know. If you have a graph of a certain average degree, then you will always find a subgraph of your graph that has a nice minimum degree, which is about half of what you had as the average degree, and you maintain the average degree in your subgraph. So how do you find this subgraph? This is just, you go deleting vertices with 2 low degrees, 1 by 1, and you can calculate that you will not delete everything. You will end up with a non-empty graph H that has these properties. So it's really easy to prove lemma, perhaps you've seen it around. So if you apply this lemma in this situation to a graph with this minimum degree, average degree, then I find myself exactly in the situation from the page before, where I have this minimum degree. So I can just prove this what they have. So now I'm going to ask and this is also, it's sharp, like it's tight, because you could just have a collection of complete graphs that are just too small, that just have size k, like k vertices, and you cannot find a k edge path, which would mean k + 1 vertices, right? So what I want to know now is, this is talking about paths. So how about if I want other trees? So I want to get to some statement that uses some conditions like Dirac or like this Erdős-Galay theorem, but instead of the output being a path, I would like to see trees. So this has also been done. So there is, it's not been done, but it has been conjectured there is the Erdős-Sors conjecture, which says if I have average degree at least, well, it's k minus 1, strictly greater than k minus 1, but I mean, let's maybe not even care so much about minus 1 is here. So about k, then I have every tree with k edge as a subgraph. And now this is every tree and of this size. But this doesn't mean that they are all there and they are all disjoint or something. It's just you say, which tree do you like? So you want to have a path, you want to have a star, you want to have a binary tree, you want to have whatever, like a comb, like whatever tree you want that has this number of edges, we can find it in there. And it's also not necessarily induced or anything. It's there, like a path. So what's known about this conjecture, so and note it's exactly the same condition as in the Erdős here. So what's known that it's a proof has been announced like in the 90s, but there's no manuscript written down, so it's sort of still being worked on by other people. So it's true for special classes of trees and host graphs, or some special classes, and we showed it for large graphs where k is linear and the number of vertices of the graph, so the graph's sort of dense, and the maximum degree, this is the maximum degree of the tree is bounded by something. So it's not completely resolved, I would say. Yeah, there is a similar version also by Rosen, which has a better bound here, but is only approximate. So this is something that is known. So I want to tell you something else, which is, so what if I would weaken this? So if I would, this is a conjecture, and if I would weaken it, we could say this, right? Thinking again of this folklore lemma that we had earlier, if I just ask, like if I make a greater assumption and say the average degree is this much, and we use this folklore lemma, then we get the minimum degree in a subgraph. Then I just look at the subgraph because I don't care where the tree is, right? I go to the subgraph with that minimum degree, and then we can embed it greedily in the subgraph, right? Because if this is like, this is my subgraph H, let's say, and this is my tree, then I'm just going to go vertex by vertex, and this minimum degree is going to be enough to put down any tree. I will just go one by one through the tree, and I'm just going to embed it. So this is really easy if you weaken this in this form. So it's just a factor of 2, where we just have to see if one can really do it. So this bound here can be lowered a little bit, but it's like a ridiculously small factor that is the gain here. So I don't think it's really known for something like, I don't know, 1.5K or something like that. I don't think that is. So in the same way, so let's go back again to the to this observation with this folklore lemma. If we could show that a graph of this minimum degree here, like about k half, has every kh tree, right, then that would imply this Erdős-Sors conjecture in the same way as we had with this Erdős-Galai theorem for the path, right? I'm just really going through this. So, but this is not true. Like, you cannot just show this thing here. This is not going to be true because, first of all, what are you going to do with vertices of really large degree in the tree? If they give you a tree and the tree has is just a star, or it has one vertex of really high degree, then there is no way. If there is no such vertex in G, then there is no way to embed it there, right? And the other problem is, we've seen this a bit before, the other problem is the components of G, they could be just too small. If I have this minimum degree, then basically I could have G could just be union of really small, sort of this size plus 1 components. They are complete, but the tree T will not fit in. So that's like the 2 problems that you have. But now people said, yeah, but maybe I could just not look for any tree, but I could just look for bounded degree trees, right? That should be easier. And then this first problem is not a problem anymore. That's good. So you just bound degree, let's say constant degree at most, right? There is some constant, and that's how much. That's about the maximum degree of the tree, and then you can try this thing. But still, you have the other problem. But now you can say in this Dirac situation, where you actually want something that is the same size of the graph, so it would be a spanning tree, right? It was a Hamiltonian path for Dirac, now we would have a spanning tree. Then you don't have this problem that the components are too small, because if you have a minimum degree, about n½ if n is the size of the graph, then your graph has to be connected. So you have a component that is all, like the whole graph is just one component. So this is also not a problem there. So in this setting, with a bounded degree tree, and where this k is the same as n-1, you have, it's actually, so it has been conjectured by Bolovac, and then shown by Komno-Sharpoli and Semeredi, that this is actually working. So they have a minimum degree that's slightly bigger than this n½ so there's a little epsilon here, and the maximum degree of the tree is bounded by some constant, and so it will depend on this epsilon and delta. These two things will determine how large the graph has to be so that it fulfills this. So it's just a theorem for large graphs G, and but you can get as close as you want to this minimum degree n½ and you can have a bounded degree as much as you want, only then you'll have to pay for it with this n0, right? So this is like very common to have this kind of structure in this kind of in a theorem where you have this kind of version. So why? So this is very good, right? So because we somehow overcame these problems, although it's, I mean, you could maybe do something different. But let's first look at this theorem here. So why do we need really a larger degree than n½ So I wrote it down here again. So if you really need a minimum degree more than n½ because otherwise you could just assume you have if this is your graph, it just has like, it's bipartite and complete. And your tree is something that is like a little bit unbalanced, right? It could be something like, I don't know, short path, and then you have like, no, maybe a long path because it's degree bounded, and then you have some leaves hanging there, right? So it just looks like this, maybe the tree. Then the tree would be a bit unbalanced, right? The tree has two bipartition classes, right? It has like the class where the red vertices are would be a bit larger than the class where the other vertices are. And so it's not going to be possible to fit it into this kind of graph. So it's really necessary that we have a little bit more than a minimum degree, the minimum degree a little bit larger than n½ here. It would not work exactly. So what these people did, they investigated this more, and you can get a bit lower than this. So you can actually get to something like this, but this is then tight also. So you could, so they have a version of the theorem where you just lower this to this number, and yeah, but you cannot lower it more than that. And the other thing that you would be interested in is how about this? So the maximum degree of the tree, can this be made a bit bigger, maybe? Just maybe not all trees, but maybe it doesn't have to be that small since we have vertices of rather large degree. So they showed that you can make it this. So there is a constant so that the maximum degree of t can be bounded just by the constant times n over log n. And they have an example. So this is tight, and the example that they have is like a tree that looks more or less like this. So very often these examples of trees showing that it's tight, they have some form, like a really small diameter, and you can already see what happens. Or there is an example of a tree where you have this form. And the graph they have is just a random graph with some fixed probability, which really has high minimum degree, so even larger than n½ if you want to. But this thing will not fit. So the problem is that these small stars will not all fit. Yeah, but I don't want to go into that. So, okay, so you have this theorem, and now you may ask yourself, So, okay, this is good, but what if I really want all trees here? What about if I really want a statement, as in the Short conjecture, that says I want all trees here, like really any maximum degree. I want the stars, I want everything. And you can do that. So we showed with Bruce Reed that if you have, if you elevate this minimum degree a little bit to something like 2/3 n, so instead of n½ sort of, we now have 2/3 n, and you also add a universal vertex in the graph. So universal vertex is a vertex that sees all the other vertices, right? So it's basically saying my graph G now has maximum degree n-1, if n is the number of vertices. So there is one vertex that sees everything. Then you contain every tree of order n, so every spanning tree, and you don't have that condition about the maximum degree. So that's a nice thing. So this universal vertex, it has, for one, it covers the case when T is a star. When the tree is a star, then I'm just going to go to the universal vertex and put the center in there, and then we're done. And it also will be useful for all, if the tree has any vertex that has a degree larger than this number here, then I will also need this universal vertex. And it will also be useful, I mean, it is also necessary in other ways, in the proof at least. So that's it. So this is like another variation. So we did this, but this is actually also just a special case of, because now I want to go back down, because if you remember, this was sort of our way out of what can we do, but we were actually looking at, before we were looking at trees of a size that's not necessarily the size of the graph, but maybe smaller, some k. So then we went to this theorem, which sort of worked, and this is also in this case where it's a spanning tree. But if it's not a spanning tree we're looking for, then we have this conjecture, which is the same condition. So this is this condition just now phrased in k, because that's the size of the tree we're looking for. And the universal vertex is just the maximum degree vertex, right? So here we had a vertex of degree n-1, and here, so this is just the same as saying, right, this is the same, so this is going to be the same theorem. So in this case, it's the same. So this conjecture is not known, so we know it's approximately true, but so we have some approximate version, and there's some, so that's some evidence, but we don't know exactly. Right, and it's sort of, this is sort of corresponds to this observation where we said, if I have minimum degree this and a component of size at least k, which I would have guaranteed with the vertex of maximum degree k, then I have this kh path, which is this variation of Dirac in the beginning. So this is just like the generalization of this observation in a way, at least. Okay. So there is this conjecture. So let me just tell you some more about this conjecture, but not that much. So in this paper where we put down this conjecture, we also proved that in theory, like morally, something like this is true, because if you stay with this condition and you make this bound here bigger, so you go to some really enormous degree there, so you have one vertex of really, really large degree, then this is true, actually. And another variation, which was sort of harder to prove, was with, if you stay with this condition, so the maximum degree is k, but the minimum degree, you now do something larger, so we have something here really close to k, then it's also true. So the interesting thing is that if this was not something very close to k, but if it was exactly k, then it's trivial. The theorem is really, we've seen it in the beginning, the minimum degree, there's just this greedy embedding, so there's no problem doing this. So the problem is really if I go a little bit below this k, then it gets difficult. So because this was not, well, maybe we were not clever enough, but it was not easy to prove. So so that's interesting, and it shows that this kind of combination does work in some way. We just haven't, like, we're not there that we can really prove this. So a bit later, I mean, it appeared earlier, but it was a bit later, like that's what happens with, you know, when it appears in the journal, it's not the same as when you did it. But So we did a variation of this with my students and changed this here, this to the k-half, which is like closer to this Dirac variation. And the maximum degree then had to be a little bit bigger because, I mean, we have examples that this is all necessary. So we have examples that this is tight, we have examples that this is tight too. So I'm just not going to show them. So we have these two versions, and we have actually, so I'm not going to write it down, but we also have something in between the two versions where we let the minimum degree vary between these two numbers, and the maximum degree will vary accordingly between these two numbers. And we also conjecture that that should also have the same conclusion, that the graph contains every k-edge tree. So those conjectures are asymptotically true for large graphs and trees that are linear in the size of the graph and have a bounded maximum degree. So yeah, I'm just going to show you real quick how we showed, like, this is just an example of this theorem that shows that this is asymptotically true. So it really looks like, maybe it looks a bit horrible, so you don't even really care. So this is just, you don't even read this maybe, but it's just like we have approximately, we have these degree conditions from this last conjecture. And it's like, again, the tree is bounded, the maximum degree of the tree is bounded by some number. And you can get as close as you want, but you pay with the size of the whole thing. And yeah, so that is a theorem that I'm going to show you real vague outlines so that you just get one idea that I think is interesting, which has appeared in many of the earlier works on the tree, on these tree containment problems. So also in this Erdős-Sós conjecture and stuff. So you have a tree. Now what we will do first is that we will cut it down so we can find a constant number of vertices, which are the red vertices, so that if I take out this constant number of vertices, then I will be left with components, small components, and maybe many, like below a given vertex. But these components will all have really small size. So they will have a size that is still linear in size of the tree, but you can get it as small as you want. So this is going to be really useful because then we can embed these things, like each on their own somewhere, just using the fact that they are small and therefore they also don't include vertices of large degree and so on. And we have to take special care with these connecting vertices. But they are few, so it's going to be sort of easy. So how we do this embedding? So we apply something that is semi-regularity lemma, which you may or may not have heard of. So this is a tool that gives you a decomposition of the graph. So this would be, here's T and here's G. So this would be just, the graph is decomposed into sets of basically equal size, and the sets, there is a constant number of sets, and most of the pairs here, the edges between these two sets are as if they were random, basically. So with a small error. So this is very useful. So I will not say any more than that because I think it's not, like, maybe not the audience for going into the details, but maybe so just seen it once, even from a distance, maybe helpful to know. So then I go into this, like the reduced graph, it's just like what I see from afar when these edges, I see them as, sorry, these pairs, I view them as edges from afar. So you find a matching there, and then you will just put these small green trees, you will put them in here, in the matching edges, using this regularity that you have there. And the connections you make somehow, so I just drew it this way, it's not exactly how it is. So it's just to get a very broad picture. So there's like two things, one thing you do to the tree, one thing you do to the graph, and then you have it all organized and can do some more arguments and really put it down in there. But that's basically what you use. And the reason that in the results, I always need that the tree is relatively large compared to G, because otherwise this method here will not work. That's a detail. Okay, so I will just show you again what we've seen so far until now, because then I will go back to hypergraphs and digraphs if you don't mind. So yeah. So maybe it's also a good moment to ask a question if you have a question. Or if I already like yeah, okay. Then if you think of a question, you just ask. So so now in the beginning we saw this Erdős-Gálay theorem with path, and Dirac's theorem which I just wrote here with a path because it's all I'm interested in right now. So we have this average degree and the minimum degree condition, and the outcome is sort of similar, but here it's in the whole graph, and on this side it's just k, which is something that may not be equal to the size of the graph. So then we said there was this variation in the middle. That was something that we saw then, right? And then there was the Erdős-Sors conjecture, which generalized this thing here to trees. So now this below this line, we will talk about trees now. So also below this line, we had the Comro-Charcot similarity theorem, which had this very similar to Dirac's condition, and talks about spanning trees with bounded degree. And also the theorem that we have Bruce Reed that is somehow in this line as well, although it's a bit variation with this 2/3, right? So we have that. And in between, we have these two conjectures, which try to make like what I have here, like connecting these two things. These will sort of connect this with this, and this with this, right? So it's like the in-between version, trees of other sizes, but with a max-min degree condition. So if you don't want to ask anything about graphs, then I will just quickly, I think I have like at least 15 minutes, so I talk a bit about, I have 15 minutes, right? Yes.
Yes.
Yeah, I'm confused when I started, but yeah, I'll make it quick anyway. So yeah, I'll try. So okay, so let's talk a bit about hypergraphs. So maybe it was like there was lots of details now in this graph thing. So I really just want to, like, the main thing I want to talk about is this. There is this conjecture, and there are these two, which are like the more classic things, right? These, so you can forget all about these other things I told you, this stuff here. But these three theorems, sort of, they have extensions to hypergraphs and to directed graphs. So I just want to talk a little bit about those. Right. So hypergraphs. So you know what hypergraphs are? I assume. So if you don't, just imagine like R is 3. And then an edge in a hypergraph looks like this, and here's another edge, and here's another edge, and then I don't know, I can have this edge, so it's like, this is a hypergraph, right? I'm not going to go into any formal definitions, but the edges now are sets of R vertices. So it's like a graph, but you have larger edges. And, oh yeah, no, I lost the picture, but okay. And then you can talk about cycles and paths, and there are various notions. So it's not just one, because, well, obviously it gives you more options, but you could, let's do it with 3 better. So one option is tight cycles, tight path. They look like this. You have, so I hope you can see, it's really hard to draw hypergraphs. So, they look like this. So you just have to really intersect a lot the edge that came before you. So you have like a linear order for a path. You have a linear order on the vertices, and every 3 consecutive vertices form an edge, or every R if you are in the general case of an R uniform hypergraph. I just draw it with 3, right? And if it's a cycle, then you have to sort of close up at the end. So that's my definition. I'm not going to give you a formal definition, but that's what a tight path looks like. So just have an idea. And then the degrees are also not like usual, but you have to talk about co-degrees, or I mean, you have different options, but one that is used a lot is co-degree, which is, you write it like this, and it means every R minus 1 tuple, which, I mean, let's say R equals 3 again. So if you are this tuple, you look at this tuple here, it has to have a lot of edges going on. So it's this the degree. Yeah, I don't know why didn't I could exactly write is equal this is equal, and this is exactly. So I don't know why I wrote this with at least, but yeah. So the thing is, this tuple here, this pair has co-degree 3 if there are 3 edges like this, right? So there are this sort of adjustment, and there are certainly other options to do in hypergraph, but it turns out usually finding the tight structure, well, the loose structure is something you can imagine where I don't want to define, but the tight cycles and parts are usually the most difficult to find, because you just need so much like connection, intersection between edges, right? And so you need these co-degrees, which are in some way the strongest type of degrees also you can define. So what exists is we had Dirac's theorem, and there is an extension for hypergraphs of Wojciechowski and Semerady from 2008. So they show which is basically the same. I mean, you have a little extra term here, but you also have the Hamilton side cycle, which is just this type of cycle I just showed. Then there was this Komroshakovsky and Semerady theorem, and we've shown this. So this just like from last December. So this is like the result I'm most excited about right now. So we showed an extension of this Komroshakovsky Semerady theorem to our uniform hypergraphs. So now there is one more term here. We talked about the co-degree, but there is also the maximum degree of the tree, which in this case is just the maximum number of hypergraphs a single vertex belongs to. So this is a type of condition we use here. And then I also didn't say what an R tree is. So that is a hypertree, R uniform hypertree, which I will just define like this. So if you look at normal trees, trees and grass, then you can describe them if you want. You start with an edge, and then at any step, you just add a new vertex and add an edge to an earlier vertex. So it's going to look like this. And I'm going to add one here. Then I'm going to add one, I don't know, here. So you just go on. This could recursively define a tree. You could define trees like this. I mean, maybe you don't have the tree that is just one vertex in this case, but maybe you don't have that one. So this is a way of defining trees in graphs, in normal graphs, so uniformity too. So in hypergraphs, you can do the same. You can just start with an edge, and then you say every new edge has to intersect one of the previous edges in R-1 vertices, and the rth vertex is a new one. So you just go and add new edges everywhere, right? So this is like very intuitive definitions of trees and hypergraphs, and also works very well if you think of how we define tight path and hypergraphs. It seems like to be the appropriate concept if you look at corresponding trees. So these are all R trees. So with this concept we've shown, and then I show you like a real quick glance at the proof, but I promise it's just half a minute. So I just want to show you this picture basically because I drew it for some other talk. I really like it. So you cut the hypertree into small pieces, which means that now your hypertree will look like really a bit wild, like this. And now instead of cutting at a vertex, we cut at pairs. So we have these pairs here where we cut. But you can really do it very similarly to the way you did in trees. It's just a bit more complicated to do, but you can do it. And then you have these small trees that are now hypertrees as well. And then there is some version of hypergraph regularity, and you use some extra arguments that I don't want to go into it all. So it's just that the proof in the end sort of follows the scheme of the other proofs. So that was this theorem here. And now I'm gonna, and there's still the Eddy-Schurz conjecture missing, which is, this is the Eddy-Schurz conjecture reformulated instead of saying average degree, I'm talking about number of edges is this, because, sorry, there's something weird here that I don't know what I'm meaning. So yeah, there's a parenthesis missing, right? This is it. So there's a parenthesis missing, and And there is a version for hypergraphs, which is Calais conjecture, there's not much known about it. So it says just the same. If you look at this will give exactly the same number as this one. If you set R equal to 2, which is the graph case, right? So this is Calais conjecture, and there's not much known about it. So there are some special cases, like trees that look very much, so it's the same type of trees before, trees that look very much like stars and yeah, some special case. Right, so that's hypergraphs. I'm gonna real quick look at digraphs, I think. So we look at directed graphs or digraphs, which are just, now you have directions on the edges, which you've probably seen digraphs before, but I mean, there are maybe slightly different notions. So we will not have loops, and we will not have parallel edges in the same direction. So that means if you have an edge, right, like this, you can have this, but you should not have this, right? So I don't want this, but you can have 2. But you can also have just one edge between 2 vertices, so no problem at all. So it's going to look like this. And the in or out degree of vertex is just the number of edges leaving or arriving at the vertex, right? So that's the degree notion that we have. So we have to just clarify this first. And then with this, there is some kind of variant of the short conjecture, but it's very similar. So you again have the number of edges, which will give you just the same notion as before. It's again expressed in number of edges, but you could also say the average out degree is k for the vertices, and the average in degree also is k. So it might look now like this is a factor of 2 more edges, and it sort of is, but this accounts for that now you have out and in degrees, and your tree sometimes just needs an out edge to go, right? And sometimes just needs an in edge. So you don't have control over that. That is the difference to the undirected case. And their conjecture is just for anti-directed trees, which are those where they look like this. Every vertex has either in degree or out degree 0. So they will really, the trees, they just look like this. So something like this. And there is a reason for that. So they cannot extend this conjecture, but since I'm like a bit short on time, I just don't want to go into this. So this is slightly unsatisfying that they have like just a special type of tree that they want to look at. So it's a slightly better situation for the other, I put this here, so I forgot. There's a slightly better, we're in a better situation for the other theorem. So if we have this Dirac, if you remember this Dirac theorem, there is a version, so which is due to these people, and actually some previous work of Debiasio and Moller. They say if your digraph has minimum semi-degree, like about n², there's a +1, but it's not always necessary, but yeah. If you have this minimum semi-degree, which means the minimum over all in and out degrees, then you have every oriented Hamilton cycle. And so that means not only the directed Hamilton cycle, but also the one that goes, I don't know, 3 edges going ahead and then 2 edges going backwards and then an edge going forward and then, I don't know, like whatever orientation you want, you can find. So that you can find any orientation. And there is a variant of the Konrad-Sarkozy similarity theorem for digraphs, which says, again, you can find any orientation of any spanning graph. You bound the maximum degree this way. And what you need is, again, this minimum semi-degree condition. So it's somewhat, the degrees are larger because you want about n½ out edges and n½ in edges. And your graph has size only n, but the edges can overlap, sure, right? You can have in and out edges to some vertex. So, but these theorems do extend. So I think that's nice. So you got this? Yeah. So yeah, I don't say that, I think. So yeah, just I have some questions. So I would like to know how about these things in the middle that we had, where you said we had something very similar, which I called the Dirac variation or something like that, I called it, right? So can you do the same for in the digraph? If it's a component large enough and you have this minimum semi-degree, can you find the any oriented KH path? Which I think is an interesting question. And it is, you could say only in oriented graphs instead of digraph, where oriented graphs don't have any parallel edges at all. So it makes it a little bit easier because you automatically, with this semi-degree, you get a large enough component. So it's just a variation. So, and this is true for directed path. And it's also true if we lift this a bit for anti-directed path. So there is some evidence that you could do the, well, in this slide we had all the theorems, that you could do these things that you had in the middle for directed graphs as well, but it's very, very open. So I'm just gonna leave it at this. So you could also ask it for trees, but I think I'm just running out of time, so I'm just not gonna say it. So I had some final remarks, which basically I could say some more about this. The Schurz conjecture for other orientations would be nice. And for the hypergraphs, there would be, so for one, in the theorem that we had this bound on this maximum degree on the tree, which of course you could ask, how about other degrees? Like, could it be other degrees? And maybe more interesting, how about making this bigger? Because you remember in this Komlov-Shrakoli-Semerely theorem, they have this degree that is not a constant anymore. They have this n over log n, right, times a constant. So maybe you can do this too. But I mean, you could not get better than that. This we know from the same example. Then, there's another question that in the same theorem, we have this spanning tree and they have this Hamilton cycle with the same co-degree condition. And you could now ask, where I just said very quickly, I said you could consider other degrees, right? So we consider this co-degree, which talks about R-1 tuples having a certain number of neighbors. You could look at smaller tuples, so you can define other degrees, and we believe, so there is something known in this direction for the Hamilton cycles, and we believe the spanning trees should have the same thresholds there. So then, maybe I just don't get into it. Yes, and so we think it should be the same, and and then maybe as a last final remark, like really the last thing is, if we go back to the graphs, so I just really like to say that we had this theorem. If you remember, you have a huge maximum degree and you have minimum degree 2/3 K, then you contain every KH tree. And this, of all the results, has the easiest proof. It's just a page. It's not, it's not obvious either, but it's really not a difficult proof. And we did not manage. I think it should be true to lower this, since you have this really large degree. Also, in view of the other conjectures it should clearly be true with this number, or some bit smaller number than this 2/3. And I don't know. So maybe there is some kind of easy proof for a theorem where this is K-half. And that would be really nice to know. So if you want to look at something, this is not too hard and does not use regularity or anything really difficult. That's just to encourage you, if you like to think about it. So, and if you want to learn more, I wrote a survey some time ago, and it treats many of these questions, and there are some problems in it, and also just the history of how everything, how all these things play together, and implications and so on. So if you want to look at this, then you can just Google it, find it on the archive or on my homepage. So yeah, that's it. So I thank you very much.
Merci, thank you. And we have very recent results on your paper. Are there any questions or comments?
Maybe just a small question, Maya. It's very nice, I mean, to have all these relations and all these properties, I mean, on graphs and digraphs. My question is there any, I mean, have you met, have you seen any, or have you used any application of these properties to combinatorial optimization problems or to, I mean, a real world problem, optimization problem? I agree that, I mean, all these properties are very nice. I mean, from, let's say, scientific point of view, there is no, I mean, any depth about that. I mean, this is very interesting. Just, I would like something more. I mean, I would like to see, I mean, some applications, I mean, of this to some optimization problems. And yes, I mean, we use many properties of graphs. I mean, but I am considering particularly these properties of degrees and trees. You see, I mean, there is a relation, a very strong relation, closely relation between trees and degree of nodes.
Yeah, I think it's a really interesting question, especially in your conference, of course. And I thought before this talk, I was thinking like, what can you get out of it? And I'm really not sure what you can get out of it. But yeah, I hope it's interesting. And it may be that you can have some particular problems, I imagine, where you want to have a spanning tree and you want to use it for something else. And then at least, I mean, with this, you would know that it's there. I think you can modify some of the proof so you can maybe find it, and then this can be useful. Apart from that, yeah, I'm not entirely maybe I'm not in a position to really say what example you can use it for. So I'm sorry, but but maybe just knowing things, or maybe this technique of cutting down a tree into really small pieces, maybe it's something that can be somehow useful. I don't know. Yeah, so I don't know, maybe I don't have a good answer.
Most of the properties give sufficient conditions. This means that if we have this, then we have that. If the minimum degree is greater than or equal to, I saw k minus 1/2, we have this, we have the key edge path, something like that. So, but we don't have necessary conditions. I mean, we have a tree if, or we have k edge tree only if this and this. So this may give a constraint in the formulation of the problem if we wanted to solve an optimization problem. I mean, related to these structures, to these combinatorial structures. So if you have necessary conditions, these conditions can be expressed in terms of inequalities, of constraints. And this also may be also, I mean, interesting. I mean, like a tree, we know that a tree, we should have, I mean, every cut in the graph, the tree should contain at least one edge, for instance, like something like that. I mean, it's a minimum graph, minimal connected graph, a spanning tree. Anyway, it's very interesting. I mean, because it's really, Erdos really is very, I know Erdos personally, and he really, he make, I mean, conjectures from his mind like that. I mean, if the number of vertices is greater than or equal to, and then the number of cycles in the graph is, it's really wonderful. It's really, it's outstanding. It's really wonderful. Yeah. Okay. Thank you very for your presentation. Really, it's very interesting. It's very rich. Really, many interesting properties. And if really, let me say, just finish with this. If we don't have application now, this doesn't mean that tomorrow we cannot have, I mean, a problem for which we use one of these properties. Still, we are using many properties related to graphs given by Wagner, for instance. I used many properties, composition of graphs, for instance. Composition of graphs have been characterized by Wagner. Wagner wrote a paper on this composition of graphs. And personally, I used many composition of graphs, many properties to solve combinatorial optimization problems on the graphs. You see what I mean? So yeah, always it's every time it's interesting to have some graph properties, some combinatorial properties. Thank you very much again. Thank you very much.
Thank you for coming to the talk and for inviting me. Thank you.
Are there other questions? Someone? No?
Brahim,
Oui.
Oui. Ah,
Oui.
yeah, Stéphane. Vas-y.
Comment? Qu'est-ce que tu dis, Rida?
You have a question, no?
No, in fact, I had a question which is very similar to what you have asked, Rida, but concerning optimization problems. Okay, I understand that you don't have necessary conditions, but do you have even partial necessary conditions?
I think it's very hard because if you have like a tree, I mean, if you look for a specific tree, like a path, and I mean, it's really hard to say what anything contain, like lots of things contain a path.
Yeah.
And yeah, but I of course, if you say you want to contain all trees, there has to be maybe. Yeah, no, I don't. Yeah, no, I don't know.
Oh, okay. Because in terms of optimization problems, there is the minimum cardinality constraint, minimum weight cardinality constraint tree, for example, which is a direct application to what I think it's a direct application of what you have presented. And there is also the hop constraint paths, minimum weight hop constraint paths, where you are looking for existence of the path from S to T, from a node S to T, which uses a bounded number of edges. That's why I'm particularly interested in necessary conditions for translate these conditions, for being able to translate these conditions into constraints that will be used in linear programming, for example. So
yes,
that's in terms of applications, but very interesting. I think we should be able to learn more on these subjects, and maybe we will be able to translate these properties into constraints. That will be very useful, I think. Thanks.
Thank you.
I think in the future we will surely use these conditions for some practical problem or for a polyhedral context.
I think what is interesting is that there is a lot of properties.
Yes,
yeah,
and conditions on trees, and we are sometimes use trees the connectivity for the connectivity of
Okay, good.
So thank you very much for your presence and your talk. That was very interesting, and I hope that you enjoy this optimization days, and you can stay with us tomorrow to have an idea of the work of our students also.
Yes, I will. The only problem is we have 6 hours of time difference. So.
Perhaps after midday here. Yes, I know. Good morning. I have to say to you, not good afternoon.
Yeah.
And let's hope next time you will be physically in France.
Yes, I hope.
I mean, next time maybe the pandemic will be will be gone, and you will be physically in France, maybe. Huh?
Yes, I hope. That would be fine.
Thank you very
And
much.
you here.
Thank you, and have a nice day.
Yes.
Okay, so we finish the session today, and tomorrow we'll start at 9 o'clock.
9 o'clock, yes.
Okay, good. Okay. Okay, thank you. Okay,
So
so have a good day and see you tomorrow.
yes.
See you tomorrow. Bye-bye. Bye-bye.
Goodbye, everybody.
Bye-bye.
Ok.
Demain, il y a ce qu'il faut pour...
Attends, je vais déjà arrêter l'enregistrement. Hop, voilà.
Voilà, c'est mieux.